Greetings, Earthlings! Before we start exploring, don't forget to like, comment, and subscribe, wherever you're listening. It helps more people find the show and supports our mission of making science accessible to everyone. You're here with DJ Stellar Cloud. Thank you for tuning in. Welcome back to the Exploring Your Universe radio show. Exploring Your Universe is UCLA's biggest science fair. Every year, we get over 12,000 visitors with something like over 500 volunteers. I'm DJ Stellar Cloud, and I'm here with one of EYU's lovely volunteers,
DJ Solarbeam.
DJ Solarbeam, aka Brandon Lazard, is a second-year master's student in the Earth, Planetary, and Space Sciences department at UCLA, where he is part of the SPINLab. So, DJ Solarbeam, what is the SPINLab, and what do they do at EYU?
So, UCLA SPINLab is a state-of-the-art rotating convection device that we have in the Earth, Planetary, and Space Sciences department here at UCLA. And so what we do is we have a bunch of cylindrical tanks. We fill them with different kinds of fluids, such as water, silicone oil, and liquid gallium. And we spin it extremely fast. And so...
How fast does it spin?
We can spin it as fast as about 60 RPM.
Okay.
So anything faster.
One spin per minute. No, one spin per second.
Yeah, one rotation per second.
Okay.
We do this because inside the cores of planets, as well as specifically in the Earth, the Earth has a liquid outer core.
Okay.
And
like the ocean or like the magma?
The molten core.
Okay. This is the lava right under the crust.
Correct.
Okay.
And so this liquid core is liquid, and so the Earth rotates. We know it rotates, and so what we're trying to get at is if we have a similar kind of system in the laboratory, while we're not able to replicate the exact conditions of the physics that is happening in the core of the Earth or other cores of different planets, we can extrapolate the physics that we get in our lab to see how exactly it can match that of the core of a planet or inside the core of the Earth.
Okay, so just to give our listeners a thought of the scale of this thing, we mentioned that it rotates once per second. How is the diameter or like the radius of the tank?
So we have a few different diameters that we can do depending on the experiment. We have small diameters ranging from about 6 feet
Inches.
to a foot or so. And then we can reach as tall as about almost 2 to 3 meters. Our devices are quite skinny.
Okay. So are these the devices that you guys bring to EYU? I know you guys are very famous for having a huge tank at EYU every year.
No. So we have our specific outreach tanks that are designed specifically to run anywhere that is not our lab. And so one of the hardest parts about that is that in the lab, what we have servo motors that are able to spin the tanks in the lab and spin them very fast. Yeah. But if we want to do outreach, we must have a kind of device where we have a tank that's sitting on some sort of table that can move around so that we're able to travel to different places. Yeah. And also have a sufficient amount of energy to spin it as well. So we have smaller motors on these outreach tanks. And these tanks are, instead of being super tall, they're actually pretty wide. Okay. And these tanks are about a meter.
Okay, this is the kiddie pool I was thinking of. Yep. Yeah, okay. Because at EYU, Brandon and the SPINLab have this really, really large thing of water and like food coloring. Yep. Okay, and then you spin it and you get to see the physics of how the colors move around, or what is something that you hope the kids are learning when they look at this experiment?
So typically when you have kids coming and doing, viewing the kind of science communication that like a lot of physics people will do or a lot of astronomy people will do, you either look at a telescope, or if you're doing physics, maybe you'll do like a Van der Graaf generator where your hair sticks up on its ends. Yeah. And so our goal is to try and get people interested in doing maybe something less known in like the public for physics. Yeah. Try to get them to understand and like to do fluid physics and see how that changes whenever we add rotation.
Okay, so like they get to see the tank when it's not spinning, and then you start spinning it, and the food coloring in there is going to do something different.
Yes, and so that's the big key takeaway of some of our demos that we like to do is that whenever we add rotation to fluid dynamics, a lot of the dynamics actually change. And these dynamics are the same things that happen in our atmosphere and the oceans. Because the atmosphere is just a large, it's nitrogen, oxygen, hydrogen, and the ocean is just one big fluid as well. And so whenever you add rotation, so you have these things on planets like the Earth, the dynamics are going to change, and that's what we want to showcase to these kids.
That's really cool. What are some experiences that you've had talking to the kids where you're like, oh, this kid really got it? Like, any kids that stood out to you?
Not particularly.
Yeah.
I think it was just really important to see, important to showcase how the dynamics are changing and how this is applicable to, say, something like our own climate.
Yeah.
We had a demo at EYU this year where we tried to showcase what we like to call bubble tornadoes. And so tornadoes are a product of basically a conservation of angular momentum.
Yeah.
Where you have a bunch of basically a large energy source, so like very warm weather. And because the Earth is rotating, you're essentially drawing from this like reservoir of rotation energy from the Earth, and you're transferring it into the tornado that is forming.
Yeah.
And
so the energy in the Earth is spent into the tornado.
Exactly. Okay. And so that's why you have tornadoes that spin faster than the Earth, because you have this conservation of angular momentum, where in order for it to actually form, it must spin faster than, the reservoir that's taking it from, which is the Earth's rotation.
Yeah, that makes sense. So how did you guys demonstrate this bubble tornado at your booth?
We have like the kiddie pool sized tanks that we have, but we also had a very taller one to showcase the tornadoes. And so the energy sources in tornadoes is like a lot of warm weather.
Okay.
But this is this can be equated to something like something that we call like buoyancy.
Okay, which is floating. Yeah.
So just you can think of it again as still as like warm water. And in our demos, what we do is we have a bunch of Alka-Seltzer, and this Alka-Seltzer is generating a bunch of bubbles as it dissolves in the water. And because we are rotating this tall, skinny tank, and we have this Alka-Seltzer, this buoyancy, which in turn, while it is not warm water or warm fluid in this case as it would be in like the atmosphere, the buoyancy is now being generated from these, bubbles being formed in the fluid.
Okay.
You now have this energy source in order to create tornadoes, and so we dropped a few Alka-Seltzers in. We watch as it rotates, it starts to form very skinny tornadoes, and it spins extremely fast with respect to the rotation rate of the tank that we're doing, and we got to showcase how tornadoes could form in the atmosphere.
Okay, so your booth has a colorful kiddie pool and a giant tornado.
Yep.
It's certainly one of the most popular booths at our event. I don't know if you knew that. It's certainly the most popular to photograph, and every year people come back again and again for this specific booth. So thank you for all the hard work that you and the rest of the SPINLab have put into making this booth as cool as it is. Is this your first year having the tornado?
Yeah, so what we like to do is we usually have, some demos that we like to showcase, like consistently year after year.
Yeah.
And each year what we try to do is we do, in preparation for EYU, about a month or so in advance, we do some what you could call like product testing or demo testing to see, what new thing can we try and demonstrate to the kids this year. And so this year was our tornadoes. And so we spent about a good 2 to 3 weeks for about like 2 or 3 hours a week trying to figure out how we can showcase tornadoes in a demonstration like this.
Y'all must have been looking forward to those days. You're like, my grad school work today is to test the bubble tornado. That must be fun.
It is quite fun.
And this was your second year volunteering at EYU?
This was actually my first year.
Oh, it was. Okay. What inspired you to volunteer?
So I've done a lot of outreach work in my undergraduate career.
Where did you go to undergrad?
I went to the University of Texas at Austin.
Nice. Are you from Texas?
Yes.
Wow. Okay.
And so I studied physics and astronomy, and so I was a part of an astronomy student org, and what we like to do is we got a bunch of emails to go and do outreach at different elementary and middle schools, at different state parks. And at the state parks and these schools, we would showcase a few like science demos, but we'd also have these point and shoot telescopes that we would bring out, and it was a lot of fun, and I enjoyed the work that I did in undergrad, and I wanted to do it again in graduate school, and so EYU was a perfect spot for me to do more outreach stuff.
Awesome. I mean, we're so happy to have you and the rest of the group. Can you please tell us what SPINLab stands for? I think this is a common misconception, because I always just literally thought, y'all are learning about spinning things, but it has a real acronym.
It does have a real acronym that I do not know.
Okay.
That is a mystery to everybody.
It's something Planetary Interiors.
Oh, yes, I remember. It is Simulated Planetary Interiors.
Yes, lab.
In the lab.
Okay, cool. Any other things you want to talk to us about with SPINLab at EYU?
Yeah, so in addition to the tornadoes that we had at EYU, we also had a sort of common thing that we have with the large kiddie pools, as you said, where we like to try and demonstrate a sort of instability that occurs in the atmosphere that we call baroclinic instability. And this is essentially the instability that occurs when you have the polar vortex is kind of holding in, or the polar jet stream is kind of holding in a lot of the cold weather at the poles.
I was gonna say, I'm pretty sure the polar vortex is like this crazy blizzard storm.
Yeah, it's is
that related to this?
Yes. And so you have on the Earth is a globe.
Yes.
And you have this jet stream.
Sorry for anybody listening who just learned this. Earth is spherical.
And so you have this jet stream, the circumpolar jet stream that basically travels east-west, or from west to east. And it traps both poles, both the North and the South Pole, and it traps this cold weather. And then you have the warm, like mid-latitudes and also equatorial, warmer climate at lower latitudes. And so this jet stream can eventually be broken up, and it usually is whenever you have an instability that occurs whenever the temperature differences between the pole and the equator is very large. And so this instability occurs, you get the jet stream that gets broken up, and when you have this, you have cold weather that comes into the lower latitudes, and so this is when you would have a lot of cold fronts that happen in like America. Or you would have warm weather being, transported to the poles as well.
Okay.
And so you can showcase this in like a sort of a two-dimensional model where we have our rotating spinning tanks. Except we've kind of collapsed this 3D system to a 2D system.
Yeah.
And we can showcase this is exactly what happens when you have a temperature difference in our tanks as well.
So do you guys heat one part of the tank?
We actually cool the center of the tank, and so you have warmer waters compared to the center of the tank.
Okay.
And this temperature difference is what we showcase as a baroclinic instability.
That's really cool. Okay, so the tank's spinning, the center's cooled. They get to learn about jet streams and general like current dynamics. That's funny, current events, current dynamics, because the Earth spins and the Earth's got different temperatures going on, and it's extremely colorful. And they have the tornado. Anything else about the SPINLab booth that we missed?
Yes, we also, it seems like we do a lot of things, and we kind of do.
Yeah.
We had another part of our booth, this kind of outreach sort of initiative called DIY-namics. And what DIY-namics is supposed to be a cost-effective way of, high school teachers or kids to be able to perform some of these fluid demonstrations on their own, and also on a smaller scale. And so we had a few of these DIY-namics kits that we like to call them, and these kits are pretty cost-effective. All they need is a Lego spike kit, and so Lego has these kits where you get to program. You can program the small computer, and you can rotate a very small, again, cost-effective small rotating tank.
You can add your mini SPINLab at home.
Yep, you can add your own food dye and see exactly what happens. And there's a bunch of videos on the YouTube channel, the DIY Dynamics YouTube channel, as well as a bunch of different news articles and papers that people can point to see how exactly they can use these kits and just play around and have fun.
That's awesome. Are you a YouTuber?
I am not. I say that, but I did have a YouTube channel back in high school where I posted like a few videos of video games, but that was it.
Okay, what are the video games?
I am not going to reveal that here.
Okay, that's fair. I used to play League of Legends, so it's not going to get any worse than that. But anyway, the SPINLab is crazy, and I love that part of it is you can take your own mini SPINLab home. People always want more EYU throughout the year. That's part of the reason why we launched the radio show, but I think it's really cool that they get to take a piece of the science home with them. Let's talk briefly about the director of the SPINLab, Professor John Arnaud. Am I pronouncing his name correctly?
Correct.
I had no idea that he was so passionate about outreach. What other kinds of outreach events is he leading for your lab?
Currently, it was the DIY Dynamics, and as a part of the DIY Dynamics, there is a course that we teach here in the department for undergraduates called Scientific Computing using Python. And so what was integrated into that course is a laboratory section where we have these spike Lego kits. And so while they're learning Python, they're also programming these spike Lego kits to perform different things to kind of showcase the physical side of programming, and seeing how exactly their programming translates to something that is physical and tangible.
Okay, so the Spike kit is like a mini robot, but you write your own code for the robot and you get to see it actually play out in person. Yep. Sort of like an Arduino, but better because it's Legos and not a microcontroller.
Exactly.
That's really, really cool, and I love that. And if you're an undergrad who's listening to this, you should sign up for this course. When is it offered?
It is offered typically every winter in our department. And it is cross-listed with the atmospheric sciences class as well. So there's a lot of spots. It's usually never full.
Why is this never full?
And we have a bunch of people that take it, ranging from physics to atmospheric sciences to math to even people who aren't in a STEM field and just want to take a programming class as well.
That's awesome. SETI class is similar, in which we also have like English majors and other people who have never programmed before join the class and learn how to program. But I'm kind of shocked that it's not always full. SETI class is usually full because people like ET. But has Professor Arnaud considered renaming this class to like Lego class? I'm just kidding, but I would never sign up for a computational class if I was not a STEM major. It sounds a little scary, but you've heard it here that it's not. And so if it's fall and you're listening, you should sign up. So the SPINLab seems like a really great place to be. How were you inspired to join the lab out of Texas?
So in my undergraduate career, I really wanted to get involved in doing some sort of research. And so I ended up, the cards fell right where I ended up being able to do research with a professor named Anna Tenarani.
Okay.
And what she does is
Anna a professor at Texas?
Yes.
Okay.
She is a physics professor at the University of Texas at Austin.
Yeah, shout out to Anna. Okay.
And she was actually a postdoc here in the department several years ago, working under Dr. Marcovelli.
Okay. Who's still here?
Correct. And I did some space physics research with her. And so space physics is kind of the study of how the solar wind interacts with different planetary bodies and just in general, kind of the physics of our solar system is what I would consider space physics.
Thank you for explaining space physics, by the way. Despite that it's in my department's name, I don't really know what space physics is. But is that what inspired the name DJ Solar Beam?
A little bit, but we'll get into the inspiration.
Yeah, so let's finish
the.
Okay, so your advisor from undergrad was a postdoc with Marco in space physics, and then what happened?
So I did a little bit of research in space physics, specifically in studying like the solar wind and what exactly that is.
Yeah. What is that?
The solar wind is kind of so we have the sun, and the sun is kind of just like spewing things out of it all the time.
Yes.
And that's what we call the solar wind. And so it's essentially just a collection of charged particles being spewed from the sun. Mm-hmm. And it interacts with things like the Earth's magnetosphere. And so sometimes whenever it interacts with our own magnetosphere, we can get things like the aurora, or we get space weather. And it also interacts with, things that we put up into space, like satellites, GPS satellites, and other things.
Okay.
And so this got me really interested in studying the sun. And so while I wasn't directly studying the sun, I got interested in studying just, anything about the sun. You have things as far away as like the solar wind. You can get to things like different layers of the sun. And so what I was most interested in is the interior of the sun.
Okay.
And so you have the core of the sun where you have fusion happening, is generating the energy that we see. You then have that energy that is moving out of the core of the sun into another layer called the radiative zone, where a lot of the energy is being transported via radiation. And then you have this outer 1/3 of the sun called the convection zone. And this convection zone is essentially just this very hot, very dense plasma where a lot of the energy is being transported via convection. And so if you think about this convection zone, the sun is indeed spinning.
Yeah. I don't think most people know that.
The interesting things about the sun is that it's spinning at different rates at different locations on the sun. And so like the equator of the sun is going to spin at a different rate than the poles of the sun.
Yeah.
And so that's an interesting thing. And so I got really interested in the interior of the sun. And so you have this convection zone where you have a bunch of, fluid. Plasma can be considered a fluid. And so you have this opportunity where the things that we do in SPINLab, where we do have fluids and we're spinning them really fast, we can somehow, find a way to extrapolate the physics that we are performing in the lab and somehow extrapolate it as far out as what's happening in the inside of the sun. And so that's what I got really interested in. And so I had the opportunity to come here to UCLA and work at SPINLab. And so that's primarily why I wanted to be here. And I thought it was a unique opportunity to study how the sun behaves in the lab.
I didn't realize that you studied the sun from the SPINLab because the P in SPINLab is planetary.
Yep.
So are you still doing solar physics from the SPINLab?
Yes.
Okay.
So the P stands for planetary, but I am pushing the frontiers of what SPINLab can do.
That's really cool. I love when you are going to force a well-known lab outside of its comfort zone. But what is the sun if not just a very bright planet?
Exactly.
We'll have the what is a planet discussion later on when we have a different guest. But that's super cool. So what is DJ Solar Beam then?
So solar, pretty self-explanatory. I like to do solar physics.
Yeah.
And I'm also a pretty big nerd, and so I like to play a lot of video games. And so the first thing that came to mind was Pokemon. I like to play a lot of Pokemon.
Oh, okay.
So Solar Beam was, of course, one of the moves that one of my favorite Pokemon uses, and that is Bulbasaur.
Bulbasaur is a Solar Beam? I only knew about Vine Whip. Okay, got it. What does the Solar Beam move actually do on a Bulbasaur?
You take in the power of the sun and you basically spew it at somebody else.
I love that. Oh, it's the big spitting one. Okay.
Yep.
I love that for you. You actually have never struck me as a nerd. I would have never pegged you as a video game player. So you learn something new every day. But I love that. My name, DJ Stellar Cloud, is actually two of my cats. So one cat is Stella and the other cat is Little Cloud. But it also is, the birthplace of stars and star formation and all that. So how did you get into astronomy?
So I really don't have a inspiring story as, some other people might have. And so I really, as a kid, I changed a lot about what I wanted to do. I knew I kind of wanted to do something sciencey. And so at first I was like, oh, I want to be like a neurosurgeon. And then,
Did you watch Grey's Anatomy?
Never.
Okay, then what inspired you to want to be a neurosurgeon?
I thought brains were cool. And brains are still pretty cool.
Yeah.
And I thought it was something, interesting to learn.
Yeah.
And then I watched the movie Interstellar whenever I was a kid. And of course, that got me interested in
Anne
things.
Hathaway? Is that Interstellar?
Yes.
Okay. I have seen it.
And that was just that was just really interesting. I've always been interested in a lot of these sci-fi elements of different books, different movies. And so whenever I took my first physics class in high school, I really enjoyed it. And I was like, I'm going to do physics. And of course, everybody loves space. So I was like, okay, I'm going to do physics and I'm going to do astronomy.
Yeah. It's okay. This story is inspiring because it's exactly like my story. And that's why I like it. I also just took physics in high school and liked it.
And I think kind of, when I go back and think about what I wanted to do as a kid, like I wanted to be a neurosurgeon, or I wanted to be, do this or do that. I think the common theme for me is that I've wanted to do something where I'm pushing the frontiers of doing something new, something that is unexplored, something that is new for everybody, and we get to learn.
Yeah.
I think the common theme is that I just really like to learn new things.
Yeah, no, I love that for you. Lifelong learner. Okay, so you have always been a lifelong explorer, and one of the things that's vastly unexplored is your universe. Not only our science fair, but also the universe in general. So you, back as a kid, maybe you weren't exactly sure what you wanted to do, but you were interested in science, so it seems likely that your parents might have brought you to something like exploring your universe. If you were a kid at EYU, what would you have wanted to hear from one of our volunteers?
I would say that you can definitely do whatever you set your mind to. And I think that is, while it is not necessarily something that I needed to hear, I think it is something that would have definitely helped me going through undergrad and graduate school, knowing that this is definitely something that I can do.
Yeah, and you are graduating, like, right now.
Yeah.
Congratulations. Do you have ideas of what you're going to do after this?
Yeah, so I just accepted a position at a startup company here in Los Angeles and Pasadena, California.
Yay, not leaving. No more Texas.
And so what I'll be doing in the next phase of my career is working at the startup company. The startup company is called Helicity Space. And what they're doing is they're pioneering this new innovative concept for an in-space propulsion device. And so what that means is essentially that if you have a device in space, you need some way to maneuver it around efficiently and cost and reducing cost. And so this new in-space propulsion concept utilizes fusion as well as some other concepts like magnetic reconnection to power different vehicles in space, to say get a vehicle from here to the moon, to Mars, and even as far as like different solar systems. And with this specific concept, you could definitely reach like a different solar system in about 15 to 30 years.
Crazy. This sounds like a very frontier pushing startup, a great place for you personally to be at. Where can people follow along with you and maybe your startup or some of your other work?
So you can head to my website, brandonjlazard.github.io.
Oh my gosh, is your last name pronounced Lazard? I'm so sorry.
It's a lot of people pronounce it Lizard, Lazard. It's
okay.
All it is a name.
Okay.
You can head to my website, brandonjlazard.github.io. You can also follow my Instagram, raisinbrand, where the I is a 1.
Oh, okay.
Yeah, and you can just follow Helicity Space and see exactly what they're doing and what they're up to, and you'll probably see me at some point.
Awesome. Well, we're looking forward to all the great work that you're going to do out at Helicity Space. And can I just say it's been lovely having you at UCLA, in case nobody else says that to you. Thank you for spending your last 2 years here.
Thank you.
And with that, never stop exploring.